Hi there, in this video we are going to tackle LeetCode problem number 141, linked list cycle. This is a classic easy level problem that tests your understanding of linked lists and pointer manipulation. What makes this problem especially important is that it introduces a real world scenario, detecting loops in data structures, which can lead to serious issues if not handled properly. So let's dive in and see what needs to be done. Let's start by understanding the problem statement. We are given the head of a linked list, and we need to determine whether the linked list contains a cycle. Now, what exactly is a cycle? A linked list is considered to have a cycle if there is a node in the list that can be reached again by continuously following the next pointer. Think of it like a circular track. If you keep walking forward, you will eventually return to where you started, right? The problem also mentions that internally POS, short for position, is used to denote the index of the node that the tail's next pointer connects to. But here is the important part. POS is not passed as a parameter to our function. We need to detect the cycle without knowing where it might be. So our job is simple. Return true if there is a cycle and false otherwise. Now let's look at the constraints. The linked list can have anywhere from 0 to 10,000 nodes. Node values can range from minus 100,000 to 100,000. And POS is either -1, indicating no cycle, or a valid index in the linked list. With those constraints in mind, let's walk through our first example to make this concrete. We have a linked list with values 3, 2, 0, -4, and POS equals 1. The expected output is true. Why? Because there is a cycle where the tail connects the first node. Remember, we are using zero-based indexing. So the node with value -4 points back to the node with value 2 at index or position number 1, creating a loop. If we were to traverse this list starting from the head, we would go 3, 2, 0, -4, 2, 0, -4, 2, 0, -4, and we would keep going in circles forever. That's our cycle. Here is our second example. We have values 1, 2 with POS equals 0. Again, the output is true. In this case, the tail, that is the node with value 2, connects back to the 0th node, that is the node with value 1. So we would have 1, 2, 1, 2, 1, 2, 1, 2, creating a simple 2-node cycle. Our third example shows the opposite case. We have a single node 1 with POS equals -1. The output is false because there is no cycle. When POS is -1, it means there is no cycle in the linked list. A single node pointing to null definitely cannot have a cycle. So now that we understand the problem, let's explore our first solution approach. We will start with the brute force method using a HashSet. This approach is straightforward and builds our intuition before we move to the more elegant solution. Let me show you how the HashSet approach works with a visual example. We will use a linked list with values 3, 2, 0, -4, 5, where a cycle exists. The tail node with value 5 points back to the node with value 2, creating a loop. The head points to 3, and the tail does not terminate. Instead, it connects back to an earlier node. So, to detect a cycle using a HashSet, we track all the nodes we visit. We initialize an empty HashSet and set a pointer called current to the head of the list. We visit each node and check if it is already in the HashSet. If not, we add the entire node to the set and move to the next. However, if we encounter a node that is already in the set, that means we have seen this exact node before, which confirms the presence of a cycle, so we return true. Now, you might wonder why do we store the entire node instead of just its value? That is because node values are not guaranteed to be unique. Two different nodes might have the same value but exist at different memory addresses. We are interested in detecting if we revisit the same node object, not just a repeated value, which is why we store the node reference itself in the set. We start with current pointing at the node with value 3. It is not in the set, so we add it and move to the next node which has value 2. Node 2 is also not in the set, so we add it and move to the node with value 0. Same with 0, it is new, so we add it and proceed to -4. -4 is also new, so we add it and move to the node with value 5. Node 5 is not in the set either, so we add it and follow the pointer to the next node. But here is the twist. Due to the cycle, the next node is the same node with value 2 that we already visited earlier. So now when we check the set, we find that this exact node is already present. That tells us we have encountered a cycle, so we return true. For the code implementation of this approach, we start by defining our method HashCycle, which takes a list node head as input and returns a boolean indicating whether a cycle exists in the linked list. First, we create a set to store the visited nodes. We use a hash set of list node objects, which gives us big O of 1 average time complexity for both adding a node and checking if it exists. Next, we initialize our current pointer to the head of the list. This is where we start our traversal. We then set up our main traversal loop, which continues as long as current is not null. If current becomes null, it means we have reached the end of the list without finding a cycle. Inside the loop, the first thing we do is check if the current node is already in our visited set. If it is, we have found a cycle and can immediately return true. If the current node is not in our visited set, we add it, marking it as visited for future reference. After adding the current node to our visited set, we move to the next node by updating current to current.next. Finally, if we exit the loop without finding a cycle, it means we have reached the end of the list. In that case, we return false because no cycle exists. As for the time complexity, this approach runs in big O of n time, where n is the number of nodes in the linked list. In the worst case, we may have to visit every node once before detecting a cycle, or reaching the end of the list if there is no cycle. The space complexity is also big O of n, because we store each visited node in a hash set. If there is no cycle, we end up storing all n nodes. And if there is a cycle, we store up to the point where we detect the repeated node. So, while the hash set approach works perfectly well, there is a technique that is not only more elegant but also legendary in the world of computer science. It is called the Tortoise and Hare algorithm, also known as Floyd's cycle detection algorithm. It is a classic and elegant way to detect cycles in a linked list. The idea is simple. Use two pointers that move at different speeds. The tortoise moves one step at a time, while the hare moves 2 steps at a time. If there is a cycle, these 2 pointers will eventually meet inside it. If there is no cycle, the hare will reach the end of the list. And best of all, this method uses only big O of 1 space. No extra memory or data structures required. Just 2 pointers and pure logic. Let's bring this to life with a story. Imagine you have a linked list with no cycles. You start from the head and move node by node following the next pointer until you eventually hit null. This is simple, clean, and finite. But now, picture a different kind of list, one that hides a sinister loop within, a cycle. If you blindly start traversing this list, you will never reach the end. You will keep walking forever. And so, the tortoise takes his first step. He begins at the head and steadily moves one step at a time. But the poor tortoise is trapped. He does not know he's going in circles, visiting the same nodes again and again, lost in an endless loop with no escape. He alone cannot detect the cycle. He is too slow to see the pattern. But then he brings along his friend, the hare. The hare is fast, twice as fast. And here is where the magic happens. While the tortoise plods along step by step, the hare leaps ahead 2 steps at a time. And in this sinister loop, something inevitable occurs. They meet. And when they do, that is the moment of truth, a dramatic realization. Whoa, we have been going in circles this whole time. That moment of collision is the definitive proof there is a cycle. And that's the brilliance of Floyd's algorithm. Simple, powerful, and unforgettable. Now let's visualize this using a linked list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Here, the node with value 1 is the head and the node with value 11 is the tail. But there is a twist. This tail node points back to the node at index 3, which has the value 4. So, what we have here is a linked list with a cycle. To better understand the cycle, imagine visualizing it in a circular form. It becomes clear how the nodes loop back instead of terminating at null. We now place our tortoise and hare at the head of the list. The tortoise is the slow pointer. It moves one step at a time using slow is equals to slow.next. The hare is the fast pointer. It moves 2 steps at a time using fast is equals to fast.next. So let's track their movement step by step. Tortoise moves to node 2, hare moves to node 3. Tortoise moves to node 3, hare moves to node 5. Tortoise moves to node 4, hare moves to node 7. At this point, both are inside the cycle. Tortoise moves to node 5, hare moves to node 9. Tortoise moves to node 6, hare moves to node 11. Tortoise moves to node 7, hare moves to node 5. Notice the hare has already completed a loop and is getting closer to the tortoise. So in the next step, tortoise moves to node 8 and hare moves to node 7. Tortoise moves to node 9 and hare moves to node 9 as well. And there it is, the moment of collision. Both pointers are now on the same node. This confirms the presence of a cycle in the linked list. As for the code implementation of this approach, we start by defining the same method signature as before. First, we handle the edge cases. If the list is empty, meaning the head is null, or has only one node, meaning head.next is null. In that case, it cannot have a cycle, so we return false immediately. Next, we initialize both our slow pointer, tortoise, and fast pointer, hare, to the head of the list. They start at the same position. Now we define our main loop, which continues as long as the fast pointer and fast.next are not null. We need to check fast.next because we are about to move the fast pointer 2 steps. So we need to ensure both moves are valid. Inside the loop, we first move the slow pointer 1 step forward. Then we move the fast pointer 2 steps forward. This is the core of the algorithm, the different speeds of the 2 pointers. After moving both pointers, we check if they are pointing to the same node. If they are, we have detected a cycle and return true. And if we exit the loop without the pointers meeting, it means the fast pointer reached the end of the list. This can only happen if there is no cycle. So we return false. As for the time complexity, since both pointers traverse the list at different speeds, the slow pointer will enter the cycle and in the worst case, take at most n steps to get there, where n is the number of nodes before the cycle begins. Once inside the cycle, the fast pointer will eventually catch up to the slow pointer. This meeting happens in big O of n time overall. And because we are only using 2 pointers regardless of the size of the list, the space complexity is big O of 1. This makes Floyd's cycle detection algorithm both time efficient and space efficient, and a brilliant solution to the problem. So, to summarize, there are 2 main ways to detect a cycle in a linked list. The HashSet approach is simple but uses extra space, while Floyd's cycle detection algorithm is faster and uses no extra memory. Mastering both methods not only helps you solve this problem, but also prepares you for more advanced linked list challenges down the road. And with that, let's wrap up this lecture here, and I will see you in the next one.